Alright, just to clear up a few things from our last video, I forgot to mention when we were talking about the third quantum number, we I forgot to mention the analogy that I like to use for the quantum number principle, the idea. The third quantum number would be the most specific location for the electron. It doesn't mean the electron is necessarily there. It just means that it spends more of its time in this section than anywhere else. So the first quantum number is kind of like the state. The second quantum number is kind of like the city. So we're getting more and more specific. The third quantum number is kind of like the street. There is a fourth quantum number called spin that we're not going to get into, but that's the most specific location for an electron. So just wanted to clear that up before we move on. All right, electron configurations. This is taught because it gives you a way to identify where specific electrons are located in an atom. It's how electrons arrange themselves in an atom. It's called the Aufbau principle or Aufbau sequence. Aufbau is a German word which is means to build. And basically what this means is the Aufbau principle says that electrons fill the lowest energy sublevels available before they move on to higher energy. So it builds up from the closest to the nucleus going away. And you have to know this sequence. There's an easy way to remember it. We'll get to it in a little bit. Let's go ahead and get all of these out here. The S sublevel, remember that's the second quantum number, S, P, D, and F, holds a maximum of 2 electrons. And that's a constant. So you just have to know, associate S with 2. S will hold 2, and S sublevel will hold 2. A P will hold 6, and a D will hold 10. F will hold 14. If you notice, as we go from 2 up to 14, it's increasing by 4 each time. It's an easy way to remember. The Pauli exclusion principle is a rule that just means that you can only have a total of 2 electrons in each orientation. For example, you remember we had for the P sublevel, we had a Y orientation, an X orientation, and we called it a Z orientation. Each one of these orientations can only hold 2. So if I can only hold 2 there, 2 there, and 2 there, 2, 4, 6, that's a P sublevel. So I can only have a total of 2 electrons in each orientation. Remember, there was a Y orientation, an X orientation, and a Z orientation. Each one of those can only hold 2 electrons. And that's the Pauli exclusion principle. So you add that up and it's a total of 6. So what would that tell you about the S sublevel? Well, if it'll hold 14 and there's only 2 electrons per orientation, then that must mean that there are 7 orientations for the F, and there must be 5 orientations for the D. So the total number of orientations is half of the total electrons it'll hold. What does that tell you about the S sublevel? Well, if that holds a maximum of 2, and you can only have 2, then what does that tell you about the S sublevel? Well, it should tell you that it only has 1 orientation, which makes sense because if you remember the shape of it was a ball, a sphere, and no matter which way you turn the sphere, it looks the same. So that is a way to remember the orientations. Hund's rule, it says electrons will fill open sublevels in the same energy level before pairing up. once each orbital is filled, electrons will pair but have opposite spins. So let's think of a p sublevel. Now, a p sublevel has, and I'm going to use what's called a box diagram for this, has three orientations. Has an X, has a Y, has a Z. Okay, this is a p sublevel. And we're going to show the electrons as arrows. All right, so 1, 2, 3. So let's say there are 3 electrons, and they're going to fill the p sublevel up. So the first electron would go there. Now, go back to Hund's rule. Electrons will fill open orientations before they'll pair up. So the second guy does not go here. He goes here, like that. And the third guy, where do you think he goes? Well, he goes here. All right. Now, what if there was a fourth electron that had to fill in? Well, then he doesn't have an option. He has to fill up. Remember, we said that the Aufbau sequence, that they will not fill up higher energy levels. This entire p sublevel has to be filled up completely before it'll move up to the next energy level. So the fourth electron would have to go here, but because they're in the same orientation, we draw the arrow opposite. And that just means they have opposite spins. If there was a fifth electron, you go here. If there was a sixth electron, you would go there. All right? And that's Hund's rule. Now, valence electrons. Valence electrons are the outermost electrons. It can range from 1 all the way up to 8. Electrons are the outermost energy level electrons. All right. Now, here's a diagram that I use in class to help my students remember how to write it. And that might be a little hard to understand. That's the sequence, the Aufbau sequence, that you use to help know what the order of lowest energy level to highest energy level is. Now, we can do it this way. I'll draw it from scratch and kind of show you how to do it. You start with the first column, and the first column is your S column. Your second column is your P column, but there's no 1P sublevel, so you start with the second one. 2P, 3P, 4P, 5P, 6P, 7P. The third column is the D column, but there's no D sublevel in the second energy level, so we thought we'd start with 3. 3D, 4D, 5D, 6D. The reason I'm not going to draw a 7D is there is no, well, there is a 7D, but there's no element big enough that reaches that far down. But if you wanted to draw a 7D here, you could. It doesn't really matter. The important is where you start at the top. The last column is the F column, so there's no F sublevel in the third energy level, so we start with 4. 4F, 5F, 6F. You could draw 7F if you wanted, but again, it just doesn't go down that far. There are enough elements to fill it in. All right, now we draw what's called our diagonals. And we start here, and we draw a line through that. And we draw a line through this, and then through here, and then here. Hopefully hopefully you see the pattern. Alright, so terribly drawn lines, but that's the way it goes. And when you're reading this, you always start here, where the X is. And whatever the black line goes through, that's what you'll write when you're writing an electron configuration.